Good afternoon. Can everyone hear me in the back? Good. So, Brian, I want to thank Dr. Brian Sam, the chair of the physics department, for inviting me to give this lecture at the 100th anniversary of the physics department. Thank you. Before I start saying some things that I prepared, I want to thank Chelsea Gendro. Without Chelsea's help, I could not have prepared the talk that I've prepared. She was able to find, as you'll see, lots of photographs that I wanted in this lecture. You've all seen the title. I won't repeat it. I want to point out this phrase, direct quote from a remarkable book. It's an encyclopedia, actually, almost a 1,500-page volume by Peter Krell. And anybody who has an interest in these topics should look at it. And that's a quote from page 699, and that says it all, actually. Okay? There are two very special individuals in the audience, and I will introduce them appropriate time shortly. Okay. So what I'm going to do is, in this talk, I'm basically going to try to connect how this research started at WSU and where it is today. So effectively, my role, what I'm going to try to do is give you a 60-plus years journey of shockwave research at Washington State University. And let me say up front that when you describe 64-plus years worth of work, you can't include everything. So please forgive me if somebody's work is left out. There's just no way. I mean, we're talking about literally several hundred man-years in a 45, 50-minute lecture. Okay, so just want to let you know. Secondly, in preparing such a talk, there is a certain amount of subjectivity involved. I've tried to be very accurate, but if you can find something that I said wrong, please correct me, let me know, and I'll try to do that. A final comment before I start on this slide. At 8 a.m. on Monday, September 23, 1968, I walked into my very first class at Washington State University as a physics graduate student. The class was mathematical physics and was being taught by Professor George Duvall. So that's when I met him, 8 o'clock, Monday, September 23rd. And George Duvall was the epitome of what you would think as a professor. He was tall, very scholarly-looking gentleman. He had horn-rimmed glasses, gray hair, and he had suspenders. He was, as I said, the epitome of a theoretical physicist. Okay. So let's see how did this start. So two individuals and one institution called the Stanford Research Institute is the reason why there is a shock physics program at Washington State University. So in 1954, there was an American Physical Society meeting in Seattle. In those days, there was only one meeting. You didn't have plasma physics, condensed matter, and all of this. This is back in 54. And there was a excursion on Lake Washington. And these two gentlemen met. And George Duvall had spent time at Richland after getting his PhD at MIT in 48. And he was at SRI. And he knew Bill, so they sort of introduced each other. And George invited William Band to come and spend time at the Stanford Research Institute. And George used to do that quite a bit. And in 1955, this is based on my conversation with George a long time ago, William Band went to the Stanford Research Institute. Keep that date in mind, 55. And Stanford Research Institute, as best as I can tell, was the only non-government laboratory in this country that was engaged in this type of research. Of course, others were the Department of Defense labs and the so-called AEC, Atomic Energy Commission laboratories. And again, to put in perspective, Livermore was established in 1953. That gives you some feel for it. So here are the two gentlemen, the pioneers, who really made all this happen. And my next few slides, my slides here today are about describing this 64-year journey. But before I do that, this is after all a physics colloquium. I'm going to give you some physics background. And let me say at the outset, the scientists in this audience will think the talk is not science enough. The non-scientists in the audience will think that the talk is too sciencey. So please bear with me. So that's what I'm going to do. But before we do that, let's talk about some scientific origins. So the scientific origins of this field are in the Manhattan Project. And here you see a picture of four very, very distinguished physicists when they joined the Manhattan Project. This is their picture taken from their badges when they joined the Manhattan Project. And thank you, Chelsea, for finding those. And this is what the gate of the Los Alamos laboratory looked like in the spring of '43. And really, the scientific origins of this field are in the post-World War II activities at Los Alamos. And I'm going to share with you three seminal papers. The seminal theoretical paper, and I think all the physicists will recognize these names. Some of you may not know Metropolis. He'd finished his PhD in '41 at Chicago and moved to the Manhattan Project. And of course, Feynman and Teller are well known. This is what Feynman looked like. And by the way, he was a graduate student when he went to the Manhattan Project. And this, in many ways, is the seminal paper in theory. And a lot of the things you read about DFT and so on, it's worth reading this paper. To the best of my knowledge, John von Neumann was the first person to have thought about using what he called digital machines for doing shockwave problems. And this is him standing with one of his computers. And this is the seminal paper published. He'd done a lot of this work at Los Alamos, but this was when he was at the Institute for Advanced Study in Princeton. And this paper is the hallmark for all the numerical simulation that have been done since that time. And to the best of my knowledge, and I looked very hard, this is the first experimental paper in the field based on the work that was done in the post-World War II time era. So, 55. So here are the three seminal: theory, numerical simulations, and experiments. And to this day, these three are the cornerstones for much of this research. Okay, so that being said, let's talk about the science. Why should one do shockwave research from a scientific point of view? And there are two very important reasons. If you want to achieve the most extreme thermophysical condition in the laboratory, the only way to do that is shockwave experiments. There is no other way. It's a wonderful picture by Paul Drake of the University of Michigan, who, using water as a medium, has tried to make a very nice figure talking about all these things. You can see where stars, the Big Bang, the planets. And Paul plotted on this axis density, and on this axis energy, but in terms of temperature. So this is a notional plot, but it tells you about the world, if you will, or the planets or the universe, if you will. So if you want to achieve these most extreme conditions, this is the way to do it. And some of you have heard talks by people who have come from the National Ignition Facility, which is our current vice president for research used to be at. And that's what is producing lots of these things. The second reason, which is somewhat closer to my heart, is to examine physical and chemical changes in real time as they're happening. So let me explain. What shockwave research is about is you have a large slab, or what we call in physics half space. And to this half space you apply a very rapid momentum. And it doesn't matter how you apply it. Could be lasers, could be impact, could be explosives, could be magnetic field, doesn't matter. The important thing is you apply rapid momentum into half space. And if you're an observer at this point, what you will see is an initial state, ambient density, energy, and so on. You got hit by a shock wave, which is almost a discontinuity, and you get to the final state. And so, as all of you know from freshman physics, you define an impulse by amplitude and duration. So that's the amplitude, and that's the duration. About 20 years ago, people at Sandia Labs and Lawrence Livermore Lab managed to do something which was not possible when I was a graduate student. And that is change the rise time of this wave while having very, very high pressures. This allows you to do something very interesting, which I won't spend a lot of time talking about, but the reason shock waves are very, very useful is they can produce both very high pressures, very high compressions, and very high temperatures. But because of this development of what I call shockless compression, pioneered at Sandia and Lawrence Livermore, and I see our vice president has walked in. Chris Keene was at the National Ignition Facility where some remarkable work has been done. In fact, there was an experiment done at NIF about 2, 3, 4 years ago where they achieved 60 million atmosphere while keeping the material very cold. And you can call something cold dense matter. So as I said, if you want to produce the most thermophysical extreme conditions in bulk matter, this is the way to do it in the laboratory. Of course, things like this happen in nature all the time. Oh, other thing I should mention, timescales involved in these experiments range from about picosecond to a few hundred nanoseconds. And for reasons I'll be happy to discuss this with you. Except, forget hydrogen. Hydrogen is a funny atom. Apart from hydrogen, a rise time less than a few picoseconds doesn't make any sense when you talk about shock waves. So let's go a little bit further, a little more science. Why do shock waves form? So this is a typical diatomic potential, which many of you and most of you have seen. And the reason I want to show this one is Dwayne Wallace, who's a good friend. Jim knows him. So the reason you have shock waves forming is when you squeeze things, they become harder to squeeze. How many of you own a little small ball that you use to strengthen your hands? Same idea. The more you squeeze things, the stiffer they get. And that's why shock waves form. And other thing I want to point out, this is the first law of thermodynamics. Everything I'm going to talk about involves doing mechanical work. We're not pumping the electronic levels. Whether we use lasers, explosive, doesn't matter. This is what we're doing. A rapid impulsive mechanical loading. And the underlying concepts in this field are the Born-Oppenheimer approximation, which if you're taking quantum mechanics, you should know. And for those of you not physicists, it simply means it's a convenient way of solving the Schrodinger equation by keeping the electrons and nuclei separate. You can treat them as an approximation. By the way, Robert Oppenheimer, this is an interesting story, went to do his PhD with Max Born in Europe, because Europe was the center of physics till the 1920s, early 30s. You make the assumption of local thermal equilibrium. You do that, otherwise you can't define temperature. So this is very important, local thermal equilibrium. And I discovered in my studies of the last 45 years that physicists, chemists, and engineering people define temperature equilibrium differently. Being a physicist, that's my definition, local thermal equilibrium. And by the way, there are a lot of problems in physics where LTE is not valid. Okay, just want to emphasize that. I've already mentioned shock wave and shockless compression. The last thing to mention is uniaxial strain. So think about that space I showed you, half space. If this is an element in this big body, uniaxial strain simply means all of the volume that was in this space is now inside this blue space. The density has increased. But if you were to draw a diagonal of both of these things before and after, you'll notice the diagonal has rotated. That means the object has deformed also. And the challenge, and virtually every kind of material you can think of, man-made, nature-made, so on, have been studied. What is fascinating about this field, and that's why it's still around, these four things come as a package. And the time-honored technique in physics and chemistry is to vary one variable at a time and study things. That doesn't happen here. It comes as a package, deal with it. Okay? And that's what has kept people like me in business for all these years. And the name of the game is, how do you untangle the role of these variables? So one question people often ask is, why do you do this stuff? Well, as a physics professor, my answer is, look, fundamental science is the basis for all innovation applications. Hopefully all of you know who Stephen Hawking is. You can read this. And it is a field which is dominated by national security applications. And just to give you an example, the average soldier is carrying about 80 pounds of stuff. And young men and women, 20, 21 years old, are getting arthritis. If any of you in the audience can cut down the weight of the body armor by 10%, I guarantee you'll make lots of money. Okay. Tough problem. I took a crack and I failed. Okay. We study all kinds of materials. This young man who got an award just now, Travis Woltz, his PhD thesis is about converting graphite into diamond. So if you become friends with him, someday he'll tell you how to make diamonds. That, by the way, the graphite to diamond transition has very important implications for meteorite impact. And this is the interior of Jupiter. So as I said before, the only way you can create conditions like 77 million atmosphere, which people think, and 160,000 degrees Kelvin, which people think is at the center of Jupiter, the only way to do that is through shockwave experiments. This was one of the most fun shock experiments ever done. Go look up deep impact. On July 4th, Independence Day, an asteroid was impacted by an object, a projectile, which had a camera. These are the pictures that were taken afterwards, okay, or while being taken. And the whole idea was to break up the asteroid, and see what comes out. So this is a great shockwave experiment. Okay, so that's why we do it. But coming back, in academia, we do things because they're fun. Okay, somebody has to pay the bills. Okay, so I've done my part. This is what pays the bills. Let's go have fun. Now, let's come back to the journey. 1950s. William Band and two of his students start going to SRI and spending time there. Now, remember I told you the very first paper was published in experimental shock work in 1955. Later that year, George Duvall, who went to SRI at the end of 1953, had been there about a year and a half, and he writes this remarkable paper. It's a theoretical paper. But there's William Band's report I was able to find, written in July 56 at SRI. But here's the really fun part. Can you make the connection between the colors and the WSU people? I wore my crimson and gray tie today. It was bought in England. So what you see is 2 graduate students are publishing papers within 3 to 4 years after the very first paper was published in this field, first experimental paper. Pretty remarkable achievement, if you ask me. And then later in the decade, Professor William Band and Dr. George Duvall extended a rather remarkable solution by Lord Rayleigh called the permanent regime solution or steady wave solution in gases for condensed materials. It's quite an achievement. And William Band was a remarkable theorist, and he used a lot of analytic solutions to work this problem out. Okay, let's go to the 60s. Chelsea was able to find for me a picture of Don Curran from a group photograph. The reason he's looking down is he's reading something. And thanks to modern technology, we were able to find this picture. And that's a young Jim Johnson without his beard. Okay. So Jim has already been introduced. Jim, will you raise your hand? He was, as Brian noted, William Band's last student. And Jim finished his PhD in 1966. In the next slide, I'll show you something that he'd done. So these 2 gentlemen were the first PhDs in 1960. Okay. And I think the next, hopefully, Travis, you'll finish this year. We'll see. Okay. So we've been working. George Duvall joined the physics department in 64. There's an interesting story about this, and to make sure I'm not running out of time. So when William Band used to go to SRI, he asked George Duvall, George, if you decide to leave SRI and come to academia, let me know. And in 63, George Duvall called William Band and said, Bill, is the offer still open? And he said, absolutely. There were no HRS, no dean to approve. William Band was the chair of the department. George Duvall was an extremely wonderful, great physicist. He joins the physics department. And Jim told me today he helped him unload his trailer. I mean, U-Haul trailer. Okay. Right after that time, 1965, DARPA approached George Duvall and said, this is such an important field for national security. We would like you to start an experimental effort. And George had a very, Dick Fowles came from SRI, and he had finished his PhD in geophysics at Stanford, doing all his work at SRI. And that was a very common theme in those days. People were working at SRI, doing their PhD at Stanford, but really, and George effectively was their advisor. And this laboratory was established in 1968. Paul, will you raise your hand? Please. Here sits a man who played a major role in the establishment of this laboratory here. So the Impact Laboratory is established in 68, and the graduate students start doing their research for their PhD. 10 graduate students finished there, all doing theoretical numerical studies. In my mind, this is the decade that really launched sustained academic research in this country. If George Duvall, this is in a subjective opinion, if George Duvall had not come here, how many people know about nucleation and growth? If George Duvall had not come here, I'm not sure that this would have reached a critical nuclei and the field would have continued. And the physics department used to be in Dana Hall in the 50s. Sometime in the 60s, these offices were occupied by a physics faculty member. I joined the department as a student in 1968. So when I came in 68, this is where the faculty were. So here are some scientific highlights. That's a young Paul Bellamy in 1979. He still looks young to me. Don't you think, Greta? Oh, absolutely. This was the gas can that was built, and Paul played a major role in this in 1968 in Sloan Hall. This is what it looks like 51 years later. And Paul, this was a remarkable facility. It still operates just as shiny, just as well as it did back in '68. I'm going to describe just one little thing. These are some very important things that George Duval did back in the '60s. This was sort of he and William Band both were very interested in seeing how you connect wave propagation and lattices to continuum mechanics. And in some ways, this is sort of the precursor of, if you will, shock propagation in molecular dynamics simulations. The other thing is the concept of complete equation of state. A complete equation of state is a function that allows you to calculate any thermodynamic variable just by using thermodynamic identities. And there are many different ways of constructing it. Constructing a complete equation of state is part science and part art. And in my opinion, George Duval was the master practitioner of that art. And he had a whole bunch of students, including Jim, he guided. So the other thing he did was, which in my opinion, he was really the first person to do it. He was the first person to introduce how to do the mathematics of time-dependent phenomena in shock wave propagation. And this is a very simple equation. The way to explain this is, let me use Jim's thesis as an example rather than Yuki's. Yuki's not here, Jim is here. So if you take an object and squeeze it, it behaves elastically. At some point, you exceed the elastic limit and the object behaves what we call plastic deformation. And you can go home and do this. Take a piece of copper wire, bend it slightly, nothing happens. Keep bending it, after that it doesn't come back. That's permanent deformation. However, because shock waves are near discontinuous, if you hit the object very hard, you go to what is called a metastable state. You deform it so rapidly because all physical chemical phenomena take time. It doesn't realize that you've done something to it. And it goes to this state, and then it suddenly realizes, wait a minute, I can't be here. This is not where I'm supposed to be. And it relaxes towards where it wants to be. And Jim Johnson's thesis was about solutions, numerical solutions of this problem in elastic plastic solid. At the same time, Yuki Horie was working on the same phenomena in materials that undergo phase transformation, whether it's graphite to diamond or something else. And that was Yuki's work, Yuki Horie's work. So in my mind, truly these are things that were pioneered. And as I said, the experimental work, and there is Paul. 1970s. I could not find Jim Assay's picture from that era. He was the first graduate student from physics department who did an experimental PhD in 1971. This is what I call the decade of the students. 17 PhDs were granted during this decade in this field. And you can see the very broad range of things that were done. Phase transition, magnetic systems, electrical systems. And by the way, 70s is when the physics department moved into this building. I think it was around 74. Somebody must be here from, I think it was around 74, 75. Okay. Sorry? And chemical reaction. So here you see this very, very wide range of phenomena being studied and speaks to the remarkable scientific breadth of the work that was going on in that time. Let me go to the 80s. By the way, I should point out there's an interesting story. I got my PhD here at the end of 1972, and I spent a year as a postdoc with George. And then I went to Brown University for about a year, and then I moved to SRI. So I have a unique distinction of being the only one who's made that round trip. Got his degree at WSU, went to SRI, came back. Even George can't make claim to that. He only went in one direction. So I went there in January of '75, and guess who was my supervisor? The first PhD from WSU, Don Curran. Small world. And when I interviewed there in October, Don said to me, Dennis Grady, who had gone from WSU in '71 to SRI, had just left for Sandia a few months earlier. And Don Curran said to me, Yogi, we need one more WSU person. Dennis Grady just left. You have to join us. Okay. So I came here in 1981. September 81, I joined the physics department. And George Duvall actually, when I was recruited, and I was heavily recruited, George and I had a long talk, and he said, Yogi, actually I was first recruited in 78, and I didn't want to come. That's a long story, we can talk some other time. But the bottom line is I came here in 1981, and it was pretty much agreed upon that George he had decided he wanted to sort of retire, and he completed his research, pretty much his research involvement at the end of 85. And then he had some health issues, and eventually in 88 he retired. So this is what the laboratory looked like in the basement, B21, which is not too far from here if you just go down here. This is, Paul, when did the lab move here from Sloan Hall? You recall? I wasn't here. Okay. I think it was the late 70s. So we did lots of fun things. The reason I didn't want to move here in 78 when I was asked is because I started some things at SRI. These were things I was doing at SRI. When I moved here in 81, I wanted to do these things. But this is the decade where we really launched into optical spectroscopy so that you could study things at the atomic molecular level. And that's why I call it the decade where we linked continuum mechanics to classical mechanics to quantum mechanics. And one of the things that I want to highlight of this decade is, I assume most physicists know about the Ruby laser. That was the first laser made by mankind. The Ruby laser is a doublet, actually, in the red here. It's a doublet. And so we did the first experiments where we shocked the ruby, a thin chip of ruby, and you'll notice, and by the way, all shock experiments are destructive experiments. And my wife, who's in the audience, thinks I'm a kid who never grew up, because I break things and make things and break things. And I think it's fun to do that. So when the shock wave hits the ruby chip, you'll notice this doublet has moved, the wavelength has shifted. When the shock wave unloads, it comes back. In the early part of 1987, I met a remarkable, talented young physicist in India. Dr. Sharma, would you raise your hand, please? Okay. And this is 1987. And I told him I was thinking about this problem. And I said to him, do you want to come and work with me on a problem? I don't know if you can solve it or not. Okay. And he said, sure. He came. And this is truly one of the great achievements, in my opinion, of that decade. You had to combine quantum mechanics, continuum mechanics, and group theory to do the problem. It's one of the most fun scientific papers I've been involved in. And here's the thing. Here are the data, and here are the theoretical predictions. This is compression, this is tension. This is the spacing between these two lines. This was truly a theoretical problem. Do a second order perturbation calculation, all of you taking quantum mechanics 550, 551. I was giving a talk in the early 90s at the University of Washington about this work. And a very eminent physicist said to me, Professor Gupta, are those fits to the data or are they really theory? And the answer is they are really theory. Okay. And some of the data were taken after the theory was developed and applied. I consider this to be one of the most remarkable things, and this wonderful man who's sitting there, he's present now as a visiting professor. He played a major role in this. Let's go to the 1990s. So in the 1990s, there are some very interesting events. I'm going to go quickly. Lots of things. I'll describe these, but the most important thing I want to share with you, first you can see this quote from the Secretary of Energy. In 1997, the Institute for Shock Physics was formed with significant funding from the DOE. And in 1998, Matt McCluskey joined the physics department because the institute was formed. Matt, would you at least raise your hand? And this has a very interesting bearing on it. When Matt McCluskey came, he was this extraordinary semiconductor physicist who had done static pressure work. And I'll describe in a little bit thanks to Matt, we had a lot of fun doing some things. The idea was we'd done the spectroscopy, which is this scale, and this was the continuum scale. How do you approach these scales? So the way I describe this is, suppose you would take a piece of aluminum, you have magnified aluminum, you'll see grains in it. If you further magnify a grain, you will see a dislocation. That's the microscale. If you further magnify it, you see atoms and molecules. To a condensed matter physicist, the world stops there, even though I know there is something called a nucleus and there are things inside that. And yes, I do know about spin orbit coupling, otherwise the Ruby problem couldn't have been solved. But the bottom line is, by and large, this is what is called multi-scale modeling or experiments. So the thought occurred to me that how do we look at this scale? And I'm going to show you now some science highlights. This is one of my favorite pictures. By the way, I'm sorry if you're not a physicist, PRL stands for Physical Review Letters, Journal of Applied Physics, Journal of Physical Chemistry, Physical Review Letters, Applied Physical Letters. If somebody ever sells you a diamond, make sure you talk to your physics friend and say, hey, do I have a vibrational Raman line at 1332? If the answer is no, don't buy that stone. It's not diamond. Very important. However, that line, it's a vibration, is actually a degenerate line, triplet. It's a triplet. And this was the first evidence of shock wave-induced symmetry breaking. And that triplet, which is a 1332, breaks into these three. And if you shock along 100 of diamond, which is a cubic crystal, you'll get a doublet. This was Mike Boatler's thesis, PhD thesis. I call him my most expensive student because he was using platinum impactors on gem diamonds. How would you like to be that student? Okay. He did screw up one experiment. And he walked in my office and said, oh my gosh, I screwed up. And what happened? In his lab notebook, he put the decimal in the wrong place. Stuff happens. There's an old problem about temperature measurements. How many people know about vibrational spectroscopy? How many physicists know about vibrational spectroscopy? My gosh, what has happened? So the way we define temperature in a condensed system is through the vibrational levels. And the Germans have never forgiven the Indians because Mr. Raman won the Nobel Prize, and the Germans always thought that Stokes should have also shared that prize. So what happens is, and it's a very weak process. If you send 1 million photons, you'll get one Stokes photon out. So the anti-Stokes is even smaller. So this was quite a tour de force. A young man called Jerry Pangilinan worked with me, and we worked out the anti-Stokes to Stokes ratio to get the temperature out. Another wonderful postdoc with the name of Yuri Gruzdikov, a wonderful physical chemist, worked with me. And there's an old problem going back to the 50s. Nitromethane is a solvent, but it's also high explosive. If you add some things to it, it becomes very, very sensitive. And we worked out the solution to this. You can see all that. This is a record that is still not broken. Marcus Knudsen, a young graduate student, did the first picosecond spectroscopy measurements and was able to see a metastable state in a phase change. And another very wonderful, bright young student called Paulo Rigg, they shared an office, did the first X-ray diffraction measurements in the laboratory here. These were really, really impossible experiments. And I was having a cup of coffee with George Duvall. He had moved to Portland or Vancouver. And George and I were talking about some things we were doing, and he asked me, he said, Yogi, do you think they can actually do this experiment? What if they can't do it? I looked at him and I said, George, I have a backup problem in mind. Guess what? They did it. The message I'm conveying to you is, in general, I'm sorry if the faculty are offended, it's the graduate students who make the faculty look good. So these are the first X-ray diffraction measurements. done in a shock experiment. 2000s, a huge change, lots of things were done. For the first time, we measured the first measurement of X-ray diffraction for a phase change. It's published, and I'll show you that in a minute. We moved to the new building in 2003, and because of that, we were able to do all kinds of experimental capabilities which we couldn't do before. And here's the reason for Matt McCluskey. Without Matt McCluskey, I won't have gone down this direction. I don't know very much about I mean, look, I've had a solid-state physics course, but Matt is the expert. So we did some very, very fun work. Matt published lots of papers we published. And all of Matt's colleagues used to think, how does he do all this? Well, shock waves and fast spectroscopy and his expertise, and we did lots of things. So let me quickly show you. And also, this is a decade, and I'll talk about this in a second. Try to get through time. First measurements of a solid-solid phase transformation in a shock experiment using nanosecond X-ray diffraction. Potassium chloride goes from a sodium chloride to a cesium chloride structure. And by the way, those of you who may think that X-ray diffraction is very simple, you know what? Simply move the thing. These are nanosecond measurements. You can't move anything in nanoseconds. So this was, Matt, you remember this? The gallium arsenide work. The reason I showed this particular picture, I love the colors. Okay. This was a continuous, so here it's unshocked, and here we didn't put a shock wave, we put the shockless compression, and you see this change. This is the photoluminescence spectrum, and we did this. And the reason I want to mention this is, in the next decade, which I won't show, we published the first paper on quantum wells ever done in shock conditions. And I can say very candidly, if Matt McCluskey hadn't come here, I wouldn't be an author in that paper. Matt, thanks to you, you did that. This was a remarkable work again by some wonderful scientists. The first studies of a shocked high explosive crystal. And there's a comment I should make. I came to WSU to start chemical reaction work. That's what Office of Naval Research, and something in my personal life, you can talk to my wife afterwards, is the reason I'm at WSU. Okay. This is one of my favorite pictures I love to show to all the visitors. A young student walked in my office in 1999 and said, I want to work with you. I said, sure. His name was Dan Dolan. I said, how would you like to be the first person to measure how water freezes in real time? And he said, that's cool. I don't think he understood what he was saying at that time. It is cool. So all of you know about freezing water. Stick something in the refrigerator, it comes out. These pictures, the first pictures taken by mankind of water freezing in real time. So typically, I'm showing this, you put a very thin layer of water between two windows and you impact it. Nothing is happening. So liquid water and solid water are the same chemical, but the refractive index is different. So you scatter light. So every place where you see a dark region, that's where you have solid water. And wherever you see a light region, white region, that's liquid water. And Jim Johnson worked with Dan in developing the equation of state. So this is one of my favorite pictures. So if you're ever in a bar or having a beer, make a bet, ask somebody, how long do you think it takes water to freeze? Come and ask me the answer, I'll tell you, and you'll win the bet. At the same time, it was becoming very clear to me that all we could do with X-ray diffraction in this building was very limited. And that's when I started thinking about, can we go and do experiments at synchrotron? And in fact, I think Chris Keen was at DOE at that time. And the funny thing is that I knew it would take a lot of money. And the first question I would be asked is, Yogi, how do we know it's feasible? So, and I guarantee we couldn't have done it without this fish shock physics. This was a significant investment for an academic entity. We put together experiments. We got 3 days of time. These were the first measurements done at a synchrotron that established that, yes, this was feasible. Because that's exactly what happened. I went to NNSA and they said, this is a great idea, Yogi, but how do we know it can be done? The answer is There it is. And that started the ball rolling. And again, this is all published. You can see all these things. So let's go on to the next decade so we can finish. This is the decade of, there are a lot of other things we did, but I really want to talk about the dynamic compression sector. And there is Chris Keene, the big smile. He didn't write the check for it, though. Somebody else did. But this is when he was at WSU. So that's Chris Keene. That's Darrell DeWalt, who was the dean at the time. And this was the director of Argonne National Lab. This is the director of the Advanced Photon Source. This is Kathy Alexander, the high-ranking official at NNSA. And we had this ceremony. The most important thing about this ceremony is none of this. My 4-month granddaughter made her maiden trip on an airplane to come to this occasion. That's the most important thing about that ceremony. This really is the first capability of its kind anywhere in the world. It was about a $45 million investment by the US government. WSU led the effort, working with the APS and some other entities. And frankly, some 30, 40 people contributed. We got our first funding on October 1, 2011. And I was quite optimistic that in 4 or 5 years we'll be able to pull it off. It took a little longer, six years. And it's an engineering marvel. And it's a very remarkable place. There's the X-ray beam. There are all these stations. We operate this facility for the US government. And I'm going to show you, this is nice, but the real fun thing is what I'm going to show you quickly. 2010s, all the great science that came out. So this is our first measurement, the phase change in silicon. Silicon, as you know, is the lifeblood of all your whole life. Without silicon, none of this would exist. It's a cubic crystal, like a diamond, has a diamond or cubic structure. And we showed that it transformed to a hexagonal, simple hexagonal crystal. And this was quite an achievement. In real time, we published this. Then this is 2016, and in 2017, and I want to spend a minute on this. Again, there's this SRI-WSU connection. SRI was the place where the first diamonds were made using high explosives. A paper in Science in '61. And so we looked at this problem, and this is where Travis learned to do shock experiments at a synchrotron. So what you're doing is you're impacting a piece of graphite, and you're passing X-rays through it. So think of a picture you've taken where in front of the shock front you have graphite, and behind the shock front you produce diamond. And that's what you're seeing here. This is the graphite structure. This is the X-ray diffraction pattern of diamond. And these were the first measurements which showed that hexagonal form of diamond is produced in nanoseconds. Published in Science Advances. So, and in fact, Scientific American wrote an article about this, and it's been a lot of fun doing this work. Since I won't have more time to talk about, so what is Travis doing? What is Travis's thesis about? It turns out some other people have reported the formation of cubic diamond. And so I gave the assignment to Travis. I said, okay, you're a bright guy, go figure it out. Why do we sometimes get cubic diamond that some people claim? And we know we get hexagonal diamond sometime. And I'm very happy to say he solved that problem. We've submitted the paper for publication. If it's accepted, I'll tell you what the key is. Or if you can convince him to tell you what it is, he'll explain it to you. It's a marvelous piece of work that he's done. Another graduate student sitting in the audience called Pritha Ranganathan had done some work, he's a mechanical engineering student, and his data had implemented a model that Jim Johnson had developed back in the 70s in magnesium. And there's a certain kind of, again, this is a detail, don't worry about it, something called twinning. It's a way in which you can deform things. But because of Pritha's work, we knew that we could find this. We went to the X-ray diffraction capability. And even if you know nothing about this, you'll notice the spots here are very different than the spots here. That's all you need to think about. And this paper is published. You can read all this. In the interest of time, I'm going to go through. We also can do laser shock experiments where you put in you put a laser beam, you ablate the laser, you produce a shock wave, you do diffraction. This is the fun experiment, just got published in PRL a couple of months ago. So for centuries, even millennia, mankind has thought that gold was very stable, very precious, very stable. Folks, you want to win a bet in a bar? Tell people gold is not as stable. Every chemist will argue with you. But if you squeeze gold to 1.5 megabar, and Dr. Sharma sitting back there is the first author, you convert gold from FCC to a BCC structure. It's very counterintuitive. We have the data, and it's a fascinating piece of work. And there are some other things. We're working on silver and platinum. So you might say, what is wrong with these people? They work in gold, silver, platinum, diamond, rubies. We have fun. Okay. So that's really quite a remarkable thing. So this is something I want to share with you. The shock physics effort here is not just very long, has been around. It's very highly acclaimed. In 1987, the American Physical Society established the Shock Compression Science Award, the premier award in this field. And of course, the first award had to be given to Los Alamos scientists because that's where the field was invented. Guess who got the second award? George Duval. And more importantly, the American Physical Society recognized the remarkable contribution of this university to this field, and the award was renamed the George Duval Shock Compression Award. Brian, I did not receive the George Duval Shock Compression Award. It was before. Okay. But I'll happily be associated. And here's a group of people, all WSU alums or faculty, who have received this award. 7 out of the 17 awards have gone to WSU faculty or alums. That speaks for itself. And I'm not even counting the fellowships and all the other things. Just wanted to share that quickly. Today, where are we today? So I'm trying to end the journey quickly. What I want to share with you is these principles haven't changed in the last 60 years. And the most important thing I want to remark is right here. In a university, graduate education and research are linked. They're not separate, they're one. And the most important thing I learned from George Duval was to emphasis on self-reliance. And William Band was the same way. Jim, would you agree with that? And what this program has done over the last 60 plus years is produce people who are independent thinkers and self-reliant. That's the real legacy. And the effort today is covering all of these disciplines. The link between them is shock compression, and these are our partners. Because of Princeton, we are in this field. Because of Caltech, we are doing this. Because of Stanford, we are doing this. These are all partners, and the first graduate student from Caltech who's getting his PhD at Caltech, but did all his experimental work here, will be graduating at the end of this year. So yes, we have lots of partnerships. We will partner with anybody. If you have a passion for shockwave research, come and talk to us. The key is passion. This is a map of the US, and WSU is connected to all this. I'll be happy to discuss these, but just wanted to show you. We have 3 locations, and then all these institutions, national labs. So we really are a model for how you integrate across the country, how you do fun things. The future, okay? Never forget that at the end of the day, physics is about observation, hypothesis, and evaluation. It's not validation. A terrible word has gone into our lexicon now. You never validate a theory. That's just, you can't. Philosophically, that doesn't make any sense. You can evaluate a theory. There are remarkable facilities available to students. Computing capabilities have exploded in the last 20 years, but meaningful linkage with experiments is a challenge. So these are exciting times. One has access to what I call the WSU facilities are unmatched by any university in this world. Plus, we have access to lots of national facilities, you can see. So there's a very bright future, and I can tell you every student who has gotten his degree here is highly, highly recruited. Okay? We're always looking for people who are bright, creative, rigorous, and will challenge prevailing wisdom. That's a requirement. If you want to accept current wisdom, don't do this type of research, do something else. Okay. Finally, let me finish by thanking, making some comments very quickly. Again, let me remind you, I'm just the spokesman. What I've shown you is the work of some 400 man years worth of work. Okay, it's these people. It's not George Duvall, it's not Yogi Gupta. It's all these wonderful people, largely students, who have made this remarkable thing happen here. The federal agency shockwave research is expensive, very expensive. It's an expensive club to join, expensive club to maintain, annual membership. And I really want to acknowledge all these agencies who have funded this work. Of course, the university, the college, the department have been very supportive over the years. We were the first building, the shock physics building was the first building built on this campus for a research organization. And finally, if you allow me a couple moments of personal indulgence, I want to thank family and friends who've kept me grounded, but keep telling me that there's more to life than shockwave research. But my wife thinks I still have not learned that. And final comment I'll make is, and then I'll stop. I'm very grateful to 4 very special individuals for their support over decades. I have known these people longer than I have known shockwave research. 2 are my parents. The 3rd is George Duvall. And the 4th is my wife sitting in the back. All 4 of these individuals, I have known them before I knew what a shockwave was. Now, let me remind you, the reason I said George Duvall is when I walked in his mathematical physics course on September 23rd, I had no idea what a shockwave was. All I knew was I was walking a class to learn about some mathematical physics. Thank you very much for your time, and I'm going to just show this slide. You can, done. Thank you very much.